Okay, so today we're going to talk about sound intensity and loudness and decibels. So if you have, for example, here you have a speaker and it's producing sound, so it's going to generate a sound wave that will move away from the source, right? And the speaker will have a given power, so it will produce energy per unit second. So that's going to be the power of the speaker. That energy will flow away from the speaker. So typically, like a speaker, if it's a very small speaker that you use for hobby, it's going to be 8 watts. Typically, if it's a big speaker, it could be 20 watts. Okay, so 20 joule per second. Okay, and it's flowing away from the source, right? So power is the energy produced per unit second. Now, as you move away from the source, okay, what's going to happen? The same amount of energy is going to flow over a larger area. So you expect, of course, the sound not to be as loud if you are at that distance compared to this distance. And you expect the wave, the pressure wave to have a decreasing amplitude. So we talk about that last time. You have all those air molecules. You have a speaker, maybe it's 8 watts. Okay, so you have a given amount of energy that is produced per second. That energy is going to flow away from the source here. So it's almost going in. It should go in almost 3 dimensions, but you don't see it here. And what you see is that as you move away from the source, the amplitude decreases. Okay, because the same amount of energy that you start here is going to spread over a larger area. Okay, so that's why the amplitude is decreasing. So here we can define the intensity of a wave. So here it's sound wave, but it works for any kind of wave. So the intensity here will be the amount. So if you are here, for example, and this is 1 meter and this is 1 meter, so that's a unit area. So the intensity will be the amount of energy flowing through this unit area. So if you are located at a distance farther away, so maybe the distance is multiplied by 2. So maybe this is a distance d, and that's going to be a distance 2d. You see that the same amount of energy, so you have to imagine that's energy flowing here. Same amount of energy is going to spread out over. If you multiply the distance by 2, it's going to spread over 4 times the area. So if you have a unit area here, 1 meter, 1 meter, you see that the amount of energy flowing through here will be 1/4 of the energy flowing from there. So this is called the inverse square law. And I will talk about that in a few seconds, but we define the intensity of a wave as the energy flowing per unit second and per unit area. So it's going to be the power, okay, per area. So power is in watts, and then area is in meter per second. So it's going to be watt per meter per second. Power is just the energy, okay, the rate at which energy is produced or the rate at which energy is consumed or the rate at which energy is flowing. Okay? So why do I talk about inverse square law? And it's going to work the same way for light, electric field, magnetic field, radiation. You see that when you have a source here and you have some energy flowing, so if you have radiation, for example, nuclear radiation, of course, you're going to have energy being carried electric field has energy stored inside. Magnetic field, light is also carrying energy. So the amount of energy that you're going to have here flowing through this area, if you multiply distance by 2, you're going to have 4 times less energy flowing through the same area. Okay, so if you have your sensor here and you have the same sensor here, you're going to detect 4 times less energy flowing through it. So if we are talking about light, okay, so it's not, the light will be dimmer, right? So the intensity will be divided by 4. And if you multiply by 3 for the same area, it's going to be divided by 9. You can do the same idea if you have a pen here. If you are spraying pens here, you're going to have one big thick layer of pens and you multiply the distance by 2 here on that area here. So it's going to spread out over this area here. But around through this small area, it's going to be divided by 4. So the layer here will be divided by 4. The layer of pens that you get will be divided by 9. So this is called the inverse square law. Okay? So if you have that much of energy at that distance, you multiply distance by 2, you have 4 times less. And then 3 times you have divided by 9. And then divided by 16, and so forth, and so on, right? So you multiply distance by 3, the amount of light that you're gonna get here, or the amount of sound, the energy of the sound, will be divided by 9 for the same area, okay? So this is called the inverse square law, and it works also for gravity. I can show you an app. I don't know if it's just a cute app. Let's see if I can open it. You see, on Earth, Earth is producing a gravitational field in space, right? So it's changing the property of space around it. And the mass is 100 kilogram. Gravitational force is 980 Newton. Now, if I move the astronaut up, you multiply the distance by 2 from the center of the Earth. The mass is the same, but now the weight is divided by 4. If you multiply distance by 3, then the weight is now divided by 9. Okay, even though the mass is the same. So that's the idea behind the inverse square law. So let's look at the math now. So if you have a source here, that source is going to produce sound. It could be a sound, or it could be a source of light, or source of gravity, or source of radiation. You see, it's going to spread out in 3 dimensions, right, in all directions. So in that case, you can write that the intensity, so which means the amount of energy flowing per unit area, it's going to be the energy of the source per unit second, produced per unit second, divided by 4 pi r squared, because this is the area of a sphere. So it means that if you are at a distance r from the source, so if you cut out a small area here, 1 meter per 1 meter, the amount of energy flowing through this area will be equals to the power of the source. So that means the energy produced by the source per unit second divided by 4 pi r squared. Okay, it makes sense. If you have the area, if you have the amount of energy flowing through an area 1 meter square, so then if you want to know how much energy is flowing through the whole sphere here, you multiply by 4 pi r squared. So you have the same amount of energy that you have to begin with. It's going to flow through all that sphere. Okay, so it's going to be spread out all over that sphere here. Okay, so this is called the inverse square law. So you can have, that means that if you compare two intensity here, I1 over I2, that's going to be equals to R2 square over R1 square, because the area is proportional to the radius square. Okay, so it means if you want to know, if you take another sphere here, so for the same source, if now you cut out, so it's an imaginary sphere, okay? So this is imaginary. So the same amount of energy is gonna cross, it's gonna flow through that sphere, and the same amount of energy is gonna flow through that sphere. Okay, so it's gonna be the same amount of energy, except here it's gonna spread out more. So you have this equation here, that I1, so that will be the amount of energy flowing through here, I1, and you compare to the amount of energy flowing through there, so it's still 1 unit area. So if you compare I1 to I2, okay, the amount of energy here, of course, here it's going to be less since you are spreading over a larger area. So it's going to be I1 over I2 equals R2 square over R1 square. Okay? So let's use inverse square law. If you can stop the video if you want, that's my little unit area, okay? So you can imagine energy when you have a wave, energy flowing through that unit area. So if you multiply the distance by 2, then the intensity is going to be divided by 10. Okay? Because if the distance is multiplied by 10, the area is multiplied by 100. So the intensity is divided by 100. Because the same amount of energy will spread out over a larger area. Okay? So for example, if you have intensity here 10 to the negative 4 watts per meter square at a distance 1 meter. So at a distance 10 meters, so from here to there you multiply by 10. So the area, okay, so the area is multiplied by 100. So the same amount of energy is going to spread out over a larger area. So I2, it's going to be divided by 100. So I2 will be 10 to the negative 4 divided by 100. That's going to be 10 to the negative 6 watts per meter square. Okay? So that's the idea. This is applying inverse square law. And again, there is a fun experiment you can do. You take it's called the butter spray if you are very lazy. Okay, so butter spray, I don't think it's very healthy, but just for the sake of the experiments, you spray butter, right? Let's say you spray butter at a distance that you spray just one French toast, right? So the layer is going to be very thick at a given distance D. Okay, so just enough for your French toast. Now you multiply the distance by 2, so now you are 2D. And if you just put one French toast, it's going to be a disaster in your kitchen. Okay? Because actually now you can spray 4 toasts, but of course the layer here will be 1/4 of this one. So it's not going to be as thick. So the layer of butter that you get here for one French toast will be 1/4 the layer that you get here. Okay, because it's 4 times the area, so 1/4 the layer. So here, if now R2 equals 20, okay, so it means that from R1, so R2 is multiplied by 20, so I2 is going to be divided by 400. So I2, it's going to be 10 to the negative 4 divided by 400. Okay, and that's going to be, so 1/4 is 0.25, and you have a 10 to the negative 6, so it's going to be 2.5 times 10 to the negative 7 watt per meter square. So that's going to be the answer here. Here, if you multiply by 5 the distance, R2 is multiplied by 5, so then I2 is going to be divided by 25. Okay, so I don't have my calculator. So that means I2, it's going to be 10 to the, we start negative 4 divided by 25. Okay, and the unit will be watts per meter square. So that's typical conceptual questions that you can get. Inverse square law. It's very easy to have conceptual questions for AP Physics or the MCAT. Okay, so let's try this one. So this slide comes again from Johnson and Cutnell Physics. They have great slides, that's why I'm using them. And I'm using also the book, especially if you're a health science major. It's a great book. So this is the source, right? So P. So the energy from the source here, so it's flowing at a rate of 12 times 10 to the negative 5 watt or joules per second. So find the area of those surfaces here, 4 meters square and 12 meters square. So we suppose that it's okay, so we're just going to apply, never mind, we're going to apply the equation. So I1 equals the power divided by area 1. Okay, area 1 is given. So it's not like a 3-dimension. It doesn't go in 3-dimension like this one in all direction. Okay, so I don't use 4 pi r square. It's just a speaker, so it doesn't go in all direction. So it's going to be 12 times 10 to negative 5 divided by 4. So that's going to be 3 times 10 to negative 5 watts per meter square. So I2, so you see the area here between here and there, the area is multiplied by 3. So the area is multiplied by 3. Okay, so that means the intensity will be divided by 3. So that means that I2 equals I1 divided by 3, which is 10 to negative 5 watt per meter square. Or you can use the equation and you will get the same thing. So it means that the same amount of energy is going through this one and is going through that one. except this area is 3 times larger. So the amount of energy going through just one little unit area, it's going to be divided by 3. Okay? So the intensity is the energy per unit area. If it's this one, it looks like 4 times, so maybe it's not a good example. It's supposed to be 3 times as big. This area is supposed to be 3 times as big. That you get the idea. So we suppose that this area is 3 times that area here. So what do you think about that? Can we use the equation in that case? So again, this is imaginary. So all that are imaginary area. So this is an imaginary area. The sound is going through it. Can I apply this equation? In that case, the answer is no, because you see you have sound that are reflected. Okay, so it doesn't go in all direction. You have some reflection. So it doesn't work for that. That's why it makes the bathroom a very good acoustic, has a very good acoustic, right? So let's do some problems here. Now, about the human ear, um, we have an amazing device here because we can hear very, very small noise, okay, very low. And the threshold of hearing will be an intensity of 10 to the negative 12 watt per meter square. And we can hear very, very loud noise, right, with a high energy flowing through our ear per meter square. And that will be the threshold for pain. That will be 1 watt per meter square. So it's quite amazing because between here and there, you have a factor of 1 trillion. Okay, so it's a factor of 1 trillion. So this is amazing. It's working really well. Okay, so let's try to do this one. I think I forgot my calculator. So the source is a siren. So you have a siren here. It's emitting a sound. All directions. So it's going in all directions. So it's spherical. Okay, so you can imagine that the energy is flowing for an imaginary sphere here. Okay. At a distance here, the distance between here and there is 3.8 meters. So at that distance here, the sound intensity, so it means the amount of energy flowing per unit area, so 1 meter per 1 meter. So how much energy is flowing through it? Okay, is 3.6 times 10 to the negative 2 watt per meter square. So they want to find the power of the source here. So I'm just applying the equation. I is power. So if it's in all direction, so the area is the area of a sphere, so 4 pi r squared. So the power will be 3.6 times 10 to the negative 12. Okay, so that will be the amount of energy flowing through here times the area. Okay, so if you have only that amount of energy flowing through this little area here, So of course, the total amount of energy flowing through the whole sphere, you multiply by this area, which is 4 pi 3.8 squared. Okay, so the same amount of energy from the source here, produced by the source, is going to flow. It's not going to go anywhere. It's going to go and flow through that invisible sphere. That's what it means. It means there is a conservation here. The energy has nowhere to go, and it has to go through that sphere. So that will be the answer. And I think I did this one. So the power will be, you can pause the video, make sure I did that right. It's going to be 10 to the negative 10. Oh, it's a minus 2 here. So let me do the, no, I have my, let's do the computation. So 3.6 times 10 to the negative 2. Okay, multiply by 4 pi. Okay, multiply by 3.8 square. You get 6.5 watts. So a small speaker that you use, with when you do some electronics, the very small one is about 8 watts. Just to compare. Okay. So let's do the next one. And I lost my. Okay, so let's try to do this one. So it says in all directions, which means you can use the equation I1 over I2 equals R2 square over R1 square. This is just the inverse square law. So I1 is given. So you can have 2 times 10 to the negative 6 over I2 is also given. So 0.8 times 10 to the negative 6. So that's going to be equals to R2 square, which is not given, over the distance R1 is 120 squared. So that's going to be 2.5 because if the intensity is divided by 2.5, so that means the area is multiplied by 2.5. And the area is proportional to the radius squared. So this is why. So R2 squared equals 2.5 times 120 squared. And you have to take the square root. You have to take the square root. And I didn't do it, so you can do it. So it's going to be R2 is 120 times the square root of 2.5. Okay, because 2 divided by 0.8, yes, it's 2.5, that's correct. And you do 120 times the square root of 2.5, and you get about 190. Okay? So once you understand the concept, it's not that hard. So let's see. Next slide here. Okay, let's try to do this one. sound uniformly in all directions. So again, that means you can use this equation here. Uncomfortable, so that means it hurts, the sound is too loud. Okay. So that means I1 equals 3.2 times 10 to the negative 3 watt per meter square. At a position twice as far, so that means if the distance is multiplied by 2, okay, that means the imaginary area is multiplied by 4, so it means that the area, the intensity here will be divided by 4. So if you multiply the distance by 2, the intensity here will be divided by 4. And we discussed that before. So that means I2 will be 3.2 times 10 to the negative 3 divided by 4, which is 4 goes into 32 8 times, right? So it's going to be 8 times 10 to the negative 4 watt per meter square. And you can always pause the video. So the threshold of hearing is 10 to the negative 2. Okay. Below that, there's not enough pressure or force acting on your eardrum to be able to move it, right? So there's not enough pressure. Not above, below that. So they want you to find a ratio with the threshold of hearing. So this is 8 times 10 to the negative 4, and you divide by 10 to the negative 12. So that's going to be 8. Okay, times 10 to the 8. So the ear can hear from 10 to the negative 12 intensity per meter square. So that's an intensity up to 1 watt per meter square. It's quite amazing. Okay, so eardrum. You see, they talk about eardrum here. So this is the area of our eardrum. So the threshold of hearing, that means you have a power of 10 to the negative watt for 1 meter square. So if the area is 5 times 10 to the negative 5 meters square, how much energy it's going to flow per unit second through your eardrum, right? How much energy is going to hit your eardrum? It cannot flow through, but it's going to impact your eardrum. So you multiply here, right? So it's going to be 5 times 10 to the negative 5 times 10 to the negative 12 watts. Okay, so it's going to be 5 times 10 to the negative 7 watts. So because you have energy, you have a force acting on your eardrum. It's going to push and pull. Your eardrum is going to oscillate. It's going to send an electric signal to your brain that will translate that as sound. The threshold of pain is that much, right? So you have 1 watt for 1 meter square. So if you have a small area here, that's going to be the area of your eardrum. how much is that going to be? So it's just going to be 5 times 10 to the negative 1. So that's how it works. 1 meter. So here, you can try to do this one. So you multiply the distance by 20. So threshold of pain. So it means that so that means the intensity here for 1 meter, the intensity here is the threshold of pain, which is 1 watt per meter square. So if you increase the distance, and now it's at 20 meters, so that means the distance here is multiplied by 20. Okay, so the intensity here, it's going to be divided by 400. Okay, because it's the inverse square law. So if you go from 1 meter to 20 meter, the distance is multiplied by 20. So here you're going to divide by 400, right? So it's going to be 1 divided by 400 watts per meter square. So it's going to be 0.25 times 10 to the negative 2 watt per meter square. So it's going to be 2.5 times 10 to the negative 3 watt per meter square, right? So to measure how loud a sound appears to be for us, then we use a different scale. We don't use watt per meter squares, we're going to use decibels. So decibels will be called the intensity level. For us, it's going to be how loud a sound is, and it's measured in decibels. So why is that? It's because our ear is working on the logarithmic scale. The ear is logarithmic, which means you see here the intensity here in watt per meter square. If you increase that intensity just by 1 or by 2 or by 3, the ear cannot detect the change. The ear can only detect the change if the intensity is multiplied by 1.25. So the human ear is not a linear device. Okay? If you increase by just one step, by 1, by 2, it's not going to be able to detect the change in intensity, right? It's going to be detecting it only if the sound is multiplied by 1.25 or multiplied by 2. So that's why we need a different scale here, and it's called a logarithmic scale. Okay, so let me explain. Each time here the intensity is, so from here to there you see intensity is multiplied by 10. It's a tenfold. But on the decibel scale here, you increase by a step of 10. So each time here you increase by a step of 10, meaning you add 10, the intensity here is multiplied by 10. So here you increase by a step of 20. So here you multiply by 100. So each time you multiply by 10 on that scale here you increase by a step of 10. Okay, so that's how it works. It's called a logarithmic scale. And logarithmic scale is very useful. For example, if you want to compare things that are very different in size. So for example, in our world, if you compare living things or like, for example, if you want to compare atom here and human or a person here, you see, it's impossible to have all those sizes on the same scale. So you use a logarithmic scale. So one step here on that scale here means you multiply the size by 10, and this is multiplied by 10, and this is multiplied by 10. So each time you increase here by 1, in reality, you multiply by 10. So that way, you can have all those things here on the same graph. So we're going to use log in base 10. So for sound, so that will be the decibel scale here. It means each time you go increase by a step of 10, so you add 10, in reality, the sound intensity has been multiplied by 10. So we're going to go over a few examples, but just to make sure you understand what's a log in base 10. Log in base 10 of x is the exponent that you need to place on base 10 to get x. Okay, so for example, if I take my TI, where is my TI? Here. If I take, for example, log, where is my log here? Log in base 10 of 50. The number that I get will be the exponent to place on base 10 to get 50. So let's see, what do I get? I get that number here. Now if I do 10 raised to that number here, what do I get? 50. So log in base 10 of x, that's going to be the exponent that you have to raise 10 to get that number here. Okay, so of course, if you do log of 100, you get 2. Okay, because 10 raised to the 2 to the second power, it's going to be 100. Okay, so that's how it works. So we use, to measure loudness, we use a special scale, which is a logarithmic scale. And you see a few examples here. That sometime here 120, that will be the threshold of pain. Okay. And then 0, level 0 is the threshold of hearing. So how do we get that? The equation for that means the change in decibel. Okay, so the change here on that scale equals 10, the log times the log, and that's going to be the ratio between the intensity here to the threshold of hearing. So I'm going to take some example, but really what it means that if you multiply by 10 here the intensity, you increase the decibel level by a step of 10. So add 10 here, you multiply by 10 there. So for example, if you increase the decibel level by 3, what's going to happen? So you have 3. Okay, so the equation is the difference in decibel here equals 10 log, and then you have I2 over I1. So you are comparing two intensities. You can compare here to the threshold of hearing, which is 10 to the negative 12 watt per meter square. Or you can compare two intensities there. So anyway, if you have a step of 3 in decibel, so 3 decibel, it's going to be 10 log. So between two sound, if you have a change in 3 decibel, let's solve for I2 over I1. So divide by 10 both sides. So it's going to be 0.3 log I2 over I1. And again, the log is the exponent. So the exponent to place on base 10 to get inside whatever you have inside the log, right? So 10, if you do 10 raised to 0.3, you get about 2. So that means if you multiply the intensity by 2, that will correspond to an increase of 3 decibel. Okay? If the change in decibel is a step of 10, that means that the ratio between the intensity, so that will be B2 or minus B1, the ratio is 10, so you multiply by 10, okay? If the difference is 20, so then I2 over I1 equals 100, okay? So if you compare decibel here and intensity, if you have an increase of 10, intensity here is multiplied by 10. If you have an increase of 20, the intensity is multiplied by 100. If you have an increase of 30, the intensity is multiplied by 1,000. If you have an increase of 40, the intensity is multiplied by 10,000. Okay? That's because the ear is logarithmic. And why is it logarithmic? So we can hear that's such a huge range between this very loud sound and this is whispering, for example. Okay? So let's take a few examples to see. Okay, so we can use to find the intensity level. So how loud a sound appears to be, is perceived by our ear. We use a sound meter, okay? And the unit will be in decibels. So, for example, let's do the computation here just to be, to understand how it works. And we can plug that into here. So you can pause the video just to get to understand, just to make sure that you know how to use the log. So that's going to be 0 because that's a threshold of hearing. But you can use the equation. So beta, it's going to be 10 log of 10 to the negative 12. And here I'm using as the base the threshold of hearing. That's what it says here. So 10 to negative 12. So log of 1 is going to be 0. So that's going to be 0. Then here you see that you multiply by 10, right? So that means that here you can have 10. So here you add 10 when here you multiply by 10. Otherwise, you can use your equation. Here it's going to be 10 log, and here you have 10 to the negative 11 over 10 to the negative 12. Okay, so this will be 10 log of 10. Log of 10 is 1, so that's going to be 10. Okay, so from here to there, again, you multiply by 10. So here it's going to be plus 20. And you can use the equation and you will get the same thing. So from here, so for this one, for example, you can use the equation. So it's going to be beta equals 10 log, and here you have 3.2 times 10 to the negative 6 divided by 10 to the negative 12. Okay, so it's going to do we can do 10, and then log. Where is my log? Here. So it's going to be 3.2. Okay, you can do the whole thing. You can simplify, but I'm not going to simplify, just to show you how to do it. Divide by, open the parenthesis, 10, that's base 10, to the negative 12. And you get 65. Did I get 65? 65, yes. Here it's going to be 65. Okay, so this one is easy, right? Because you're going to do 10 and then log, and then you have a 10 to the negative 4 and then 10 to the negative 6. So it's going to be 10 log of 100. Okay, so it's going to be not minus 6, 12 here. Sorry. So you have a minus 12 and a minus 4, so that's going to be 10 to the 8. Okay, so remove the exponent, so it's going to be 80 log of 10, that's going to be 1, so you get 85. Okay, then 80, sorry. Then from here to there, the intensity here, from here to there, you multiply by 100, right? Multiply by 100. So it means that the step is plus 2. So that's going to be 100 dB. From here to there, it's going to be plus 20. So this is very damaging here. This is very bad. So 1 is going to be 10 to the negative 12. No, sorry. 1. So 1 here, it's going to be 10. Yes, so it's going to be log. And here you have 1 divided by 10 to the negative 12. Okay, so you can have 10 log of 10 to the 12. So 12 times 10 is 120. So that's going to be 120. And from here to there, you multiply by 10. So here you add 10. So that's going to be 140. Okay, so that's how it works. So sometimes they say this is the threshold of pain, and in another textbook they say this is going to be the threshold of pain. Either one, it's going to be very damaging for the eardrum. So this one is easy. So increase in sound level of 3 decibel. So 3 decibel, we have seen before that you multiply by 2. Okay, so that means the intensity is multiplied by 2. We did that before. Because that means 3 equals 10 log, and you are comparing two intensities here. So that's going to be 0.3 equals log, and the log is the exponent that you put on base 10 to get the inside of the log. That's going to be about 2. So if you want to amplify the sound file on a computer by 20 decibel. So 20 decibels to increase, so it means you add 20 decibel. So increase of 20 decibel step. So that means the intensity here is multiplied by 100, right? Okay, so that's how it works. So this one comes also from the book Kirkmel and Johnson. And so you have two speakers here, and so one is 90 decibel, the other one is 93 decibel. Find the ratio of intensities, but we just did that here, right? So if you have an increase of 3 decibel, that means the intensity is multiplied by 2. So this book here goes through another demonstration, so you can look at that. It's just math, but they get to the same answer. You see how they do it? They start from that definition here, with this being the threshold of sound. So they they subtract from each other. And then if you subtract 2 log, that means you divide here, and they get the same answer. It's just more complicated. Okay, so let's do a few problems, but then they all look the same. All those problems look the same. So if a difference in decibel will be 1 dB, so that means the smallest sound that we can detect, the smallest change in sound that we can detect. Okay, so 1 dB equals 10 log I2 over I1. Okay, so that means 0.1 equals 10 log, I2 over I1. So you can solve, and you get 10 raised, where is my raised, to 0.1, and you get about 1.25. So it means we can only detect sound if we can detect the change in sound only if the intensity is multiplied by 1.25. That's why the ear is not linear, because if you add 1 to the intensity, it's not going to be able to detect it. Okay? So, so here, between 60 and 100 decibel, so between 60 and 100, so you add. Okay, so decibel, you add. So between 60 and 100, you add 40. So if you add 10 for the intensity, you multiply by 10. Okay, so that's decibel, and that's intensity. If you add 20, you multiply intensity by 100. If you add 30, you multiply by 1,000. If you add 40, that means you multiply by 10,000. Okay? Or you use the equation. Okay, so that's going to be the same thing. Number 3. So that's just using the definition. It's 10 log. Here you're going to put the intensity, which is 1.2 times 10 to the negative 10. And here it's 10 to the negative 12. Right? So you can use your calculator. We're going to do 10 And then here you have the log, and then you have 1.2 times 10 to the negative 10, and you divide by 10 to the negative 12. It's about 21 dB on the scale. So you can look back at the scale here. So if you look back at the scale, decibel 20 is like very low. It's a whisper. It's about a whisper, right? 21 decibel, 20 decibel. So let's continue here. So 80 decibel, you just use the equation. So 10 log, and then, what do we have? You compare that to the threshold of hearing. So 10 to the negative 12, that's going to be equals to 80, right? So divide by 10 both sides. That means log I over 10 to the negative 12 is 8. So that means 8 over 10 to the negative 12 equals, so the log is the exponent. So this is the exponent that you have to place on base 10 to get the inside. Okay, so that means that I equals 10 to the negative 12 times 10 to the 8, which is 10 to the negative 4 watts per meter square. Okay? We have more things to do. Let's see what we have. So, by the way, let's look at 80 decibel. Where is 80 decibel here? 80 decibel, it's start to be loud. Okay, so let's keep going. So you should pause the video, okay? Pause the video and try to do them. So you have 115 decibel and 95 decibel. So that means the change in decibel is 115 minus 95. It's 20, so 20 decibel. So that means that the intensity here is multiplied by 100. Okay? So the sound intensity increases by 30 decibel. So 30 decibel means the intensity is multiplied by 1,000. Okay? And here you just plug in. There's nothing special here. Okay, so it's gonna be the decibel level equals 10, and then you have a log here. That's gonna be 5 times 10 to the negative 2 over times 10 to the negative 12. Okay, and you get, I think you get 107 decibel. Okay, so this one maybe it's more interesting. I might not do all of them, but again, you should stop the video and try to do them. foghorn, and the power, so it's a foghorn, very loud sound, very low frequency. And the power, so that means the amount of energy produced per unit second by the source, is 3 times 10 to the negative 5 watts. The distance r is 20 meters, and we do an approximation. We suppose it's going in all directions, which is not really true, but that's fine. So they want to find a decibel level of the sound. So first we need to find the intensity, which is power divided by 4 pi r squared, and it's an approximation because we suppose, I don't know, it's a special foghorn that produce sound in all directions, so we can use that equation here. So that's going to be 3 times 10 to the negative 5, 4 pi, 20 square is 400. So you have to plug that into your equation. What you get, I get 6 times 10 to the negative 9 watts per meter square. So once you have your intensity, then you can find the decibel level, which is 10, and then log, and then 6 times 10 to the negative 9. So when you have a decibel scale, you need to find to the side of a reference, right? So then the reference will be here, the threshold of hearing. So that means here it's going to be a 0, because you compare everything here relate to that threshold. So that's why you always have a 10 to the negative 12. So that's going to be 10 to the negative 12. And you get, if I did it right, 38 dB. So about 40 dB. So 40 dB. You have to check if it's correct. I'm not sure. 40 dB. Quiet radio only. Okay, so that means you are so far away that you hardly hear the sound, I guess. Okay, so the Richter scale is to measure the magnitude of an earthquake, and it's also using Richter scale, logarithmic scale. It's using So here the Richter scale use also log. Okay, so inside here we have the energy of the earthquake in kilowatt hour. So let's choose, for example. So what does it mean? For example, if we have two earthquakes and we compare them, and let's say the energy and let's say the energy is multiplied by 10. What's going to happen on the Richter scale? So I'm going to put delta R equals 0.67 log. That's going to go away, okay? Because it's a ratio. It's a ratio between the energy of the two earthquakes in kilowatt hour. And here I have plus 1.46. So if this is 10, so this is 10. So I have log of 10 is 1. So delta R equals 0.67 times 1 plus 1.46, right? So it's going to be 1.46 plus 0.67. So it's going to be 2, about 2. So that means if the energy of the earthquake is multiplied by 10, you go by a step of 2 on the Richter scale. So that's what it means. So here, for example, they want you to find the earthquake magnitude if it's releasing that much of energy. So that much of energy is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so R equals 0.67, and then you have a log here, and then you have 0.37 times 1.55 times 10 to the 10. And then you add 1.46. Okay, so it's nothing very interesting here. It's just using this. So I'm going to start by the log. So let's start with the log. So it's going to be 0.37 times 1.55 times, that's the base 10 to the 10, close the parentheses, enter, times 0.67, enter, plus 1.46. So that's going to be about 8 on the Richter scale. Okay, so then they say, so let's do the next one. So you have 2 roommates, and each of them has a stereo, and the energy flowing per unit second per unit area is 10 to the negative 5 watt per meter square. So how much louder is the music when they are both playing their stereos? So how much louder, that means the difference in decibel. So before, if it's 1, just 1, that's what you're gonna get. If it's 2, you get twice that much. Okay, because you're gonna have twice the amount of energy. So the difference in decibel will be 10 log. It's gonna be I prime. I'm gonna call that I prime over I. So this is I with 1 stereo. This is I prime with 2 stereo. So that's going to be 10 log, and then 2 times 10 to the negative 5 over 10 to the negative 5. So that's going to be 10 log in base 10 of 2. And that's going to be 3 decibel. Okay, because when actually I didn't have to do those computations. Because remember, when the intensity is multiplied by 2, okay, something that you have to remember is that the difference in decibel is 3. So I didn't have to do all of that. Okay? So if the intensity is triple, what's going to happen? If you multiply by 3 the intensity, what's going to happen? So you do 10, let's see, 10, and then log of 3, and it's about 4.8. The answer here is 4.8. Okay, so we're gonna get to Doppler effect, but next time.